So this is the first video in a set of videos dealing with Appendix A. I won't be going through the slides in a very comprehensive way in these videos. I'd like to keep the videos relatively short, just highlighting the most important concepts, most important applications that you need to note. Okay, but at the same time, I want to point you to the lecture notes. These will be fairly more comprehensive than the lecture videos. So those would be the main sort of pedagogical tool for you to consult when prepping for your assessments. All right. So Appendix A deals with a series of topics, but I'll really just be focusing on some basic probability and introducing some important distributions, as well as the moments and the estimators, and then most important, we'll be discussing inference. All right, with regard to summation, all I'm going to do is point you to the appendix of these slides, which shows you the derivation of some results presented earlier. Have a look through these, make sure you understand them, you're comfortable with moving between different ways of expressing results, because these become quite useful later on in the course when deriving the OLS estimators, as well as evaluating the assumptions and the variance of the estimators. Okay, let's discuss some basic probability concepts. I don't think it's necessary for me to read these slides to you, so I'll refrain from doing that. I'll just highlight the most important aspects of the various concepts. And when it comes to an experiment, the most important aspect that I want you to note is that it is a repeatable process. And you'll notice that later on when we talk about doing inference, we'll usually mention the phrase in repeated sampling. So in our case, usually when we don't deal with experiments in the strict definition over here, but we do deal with it in the sense of repeatedly drawing samples from some population. All right. So every experiment has some sort of sample space, which is just the set of all possible outcomes of the experiment. In the example given here, when you flip a coin 5 times, it turns out there are 32 possible outcomes in the sample space. And to figure out, to test whether that is true, check whether that is true, you can simply list all the possible outcomes, which are some of the member sets are given over here. Some of the possible outcomes. If you continue in this pattern, you will observe that there are 32 of these. Alright, a sample point is any single element in the sample space. An event is any subset of the sample space. So an event can comprise multiple sample points, as is the case over here by observing at these 2 heads. There's many ways of observing there's a number of ways of observing 2 heads in the experiment of flipping a coin 5 times. So that event comprises several sample points, whereas observing tails only comprises a single sample point. Nevertheless, it is still a subset of the sample space, and thus is defined as an event. Events can be mutually exclusive, which is when the occurrence of 2 events simultaneously is not possible. So in our 5 coin flip example, it is not possible to observe only tails while also observing at least 1 head. If one of these things happen, if you observe tails only, it necessarily means that you did not observe at least 1 head, and vice versa. So these are mutually exclusive. Events can also be collectively exhaustive, and the set of events this is the set of events that exhaust all possible outcomes of an experiment. So again, if you look at the example here, considering our 5 coin flip experiment, 6 events are defined here, those being observing 5 heads, 4 heads, 3, 2, 1, or 0 heads. Now, it doesn't matter what the outcome of the experiment is, it will conform to at least one of these events. At least one of these things must happen when we flip a coin 5 times. Therefore, these 6 events are a set of collectively exhaustive events. A random variable is a variable whose numerical value is determined by the outcome of an experiment. So this is very important to note, because think about how we defined experiment earlier on. It's a repeatable process with a well-defined set of outcomes and some uncertainty about which outcome we will observe when we run the experiment. Now, if you combine that definition with this definition of random variable, it will be immediately clear to you that in many instances, most of the variables we are interested in as economists or social scientists more generally are not strictly random variable in the way we've defined it over here. We are interested in variables, very pertinent variables, but these are not necessarily random variables. GDP is not the outcome of a random experiment. It is variable, it is uncertain, it is something we are very interested in understanding, but it is not a random experiment. It is not the outcome of a random experiment. And this is the case for most of the variables we are interested in. Okay, variables can be discrete or continuous. Examples given here: in the discrete case is flipping a coin. You can observe one of 2 outcomes, very strictly speaking, whereas continuous variables are usually defined over some interval. Although in some instances, or to make things analytically more tractable, we sometimes convert continuous random variables to discrete random variables. So height, if we just restrict ourselves to centimeters, then it becomes effectively a discrete random variable. Likewise with mass and mass. Okay, with these concepts behind us, we can define a method for calculating probability. So using the definition over here and applying that to our little experiment, we can define any number of events, and then we can calculate the probability that we may observe these events. So in the examples given over here, we've defined an event as the number of heads being 2. We know that the denominator in this instance is equal to 32, n. That is the number of mutually exclusive and equally likely outcomes in this instance. And for any given event, we just need to determine m, the number of sample points that are favorable to that event. So with the number of heads being 2, all we need to do is count the number of ways we can observe 2 heads if we flip a coin 5 times. And the answer to that turns out to be 10. So the probability of observing 5 times equals 10 over 32. And we can repeat this way of, we can repeat the application of this definition or this method for calculating probability to find the solutions to the remaining 2 questions. Okay. Then there's another way of calculating probability, because in many instances sample points are not necessarily equally likely. It happens to be the case in the example of flipping a coin 5 times. Any one of those sample points are equally likely, for the simple reason that the outcomes are all independent. The individual flips are all independent from each other. But that's not always the case. And in instances where sample points are not equally likely, we can use the following method for calculating probabilities. But probability theory and calculations not being a focus of this course, we won't spend any more time on this. The next couple of slides just deal with counting, with simple basic combinatorics, which is a field dedicated to just counting things. This is just for the sake of presenting these ideas, these concepts to students, but is not germane to this course. So if you're interested, you can look at this and try and read further into it, else you can safely ignore these two slides. Then there's just a bit of notation. I don't think there's any value to me spending too much time going through this. Just note that there are different ways of expressing certain concepts. In the case of expressing the union of two events, which can be read as the probability of observing either event A or event B, can be written as follows, as presented over here. When talking about the intersection of two events, which should be read as the probability of observing events A and B, can be expressed as given on the slide over here. Okay, the next couple of slides just list the properties of probability. Again, I won't be going through this. These are simple properties. And then these slides take you through some uses of Venn diagrams to visualize some of the ideas expressed above relating to sample space, mutually exclusive events, etc., and independent. Alright, one important concept is conditional probability, which is defined as follows. Given two events A and B, the probability that event A occurs given that event B has occurred. And in symbols, it is expressed as given on this slide. So the way to read this is the probability of observing the probability of the intersection of A and B divided by the probability of B, right? So we divide by the probability of B because we know when dealing with conditional probability that B has occurred. Okay. Now, given that definition above, it follows that if A and B are independent, then the probability of A given B is equal to the probability of A. Further, the probability of the intersection of A and B is equal to the product of the respective probabilities, that is, the probability of A multiplied by the probability of B. So on this slide, just gives you a little exercise, a simple example of applying conditional probability. And in it, a balanced die is tossed or rolled, and we are asked to find the probability that we observe a 1 given that an odd number was obtained. Okay, so event A is observe 1, event B is defined as observe an odd number. So formulating it in symbols, we can write it as follows. So we know that the intersection of A and B is given by the number 1, and the probability is, well, the intersection is 1, the number 1, and that is one sample point in the sample space. So that event is a single sample point, and the sample space in this instance is 6. There are 6 possible outcomes when rolling a die. So the numerator in this instance is 1 over 6. The probability of observing an odd number is given by 3 over 6, because there are 3 odd numbers between the numbers 1 and 6, in the range 1 to 6. So the result is 1 over 6 over a half, which gives us a third in this instance. Alright, second example is given over here. Please go through it, make sure you understand it clearly. If not, please let me know. And I think I'll end this video at this point and pick up on density functions in the next video.